Thanks, everyone. So my name is David. This is my friend Alex. Welcome to part 2 of the deep dive on state-of-the-art natural language understanding at scale. So in the first part, we saw a couple of use cases, and we did a course on how you train a document classifier, which is a fairly common use case where you have some text from whatever source. Usually you combine it with some other signals, right? So for example, if you're analyzing, customer emails, you have the emails themselves, but then you also have structured data about, who's the customer, when did they buy, what did they buy, and such. You build features, and then you try to use your unstructured features and structured features together to rank things by importance, to see what you need to escalate, to separate things by product or type of complaints or whatever may be the case. One of the things we saw in the pipeline there is that when you build the Spark ML pipeline, it's basically the same pipeline that you use both to train, based on training data that you provide, as well as to do inference. And this is also very important in the ML space, right? Because we do a lot of experimentation, right? So we set up the pipeline, and then we remove features, we change them, we play with parameters, we run tons of experiments. It's exactly the same thing in the NLP space, in the sense that you'd want to train your own custom models, and then you want to tune them, you want to customize them. One of the things that people often miss, because this library, as well as other NLP libraries, they have out-of-the-box pre-trained models. So it's like, oh, well, you need part-of-speech. Here's a part-of-speech model. You just run it. It's a one line, and you get it. And that exists here. It exists pretty much in every other library. What you need to know is that most likely, and by most likely, I mean in just about 100% of my, the projects I've experienced, it's not going to work, because you will need to train domain-specific models for your own problem. Okay, and the problem is that we as humans, we really use different languages in different occasions. So when I speak to you, I use a certain vocabulary, I use a certain grammar. Okay, when I speak to my kids, I use a different vocabulary and different grammar, and the same words will mean different things. When I talk to my wife, it's different. When I write, what I write is very different from the way I speak. The way I write emails is very different than the way I write SMS messages, than the way I write grant requests, than the way I write academic papers, than the way I write financial applications. Okay, and the result is, when you look at all those different contexts in which we speak, they actually are different languages. Okay, sometimes if you look at the healthcare space, if you look at the legal space, there really are different languages in the sense, yes, look, it will take you 2, 3, 4 years to learn how to read radiology reports, right? Or to learn how to read court transcripts, right, in a specific legal case, or how you read a specific kind of SEC filing if you're in the finance space. Okay, but even if you just look at social context, right, or specific business context, what you will need to see is that really the same words, the same characters in the same order would mean different things in different order. And what it means is that you do need different algorithms, or at the very least, you need to train your own models based on those algorithms. And a lot of the research and practice in the NLP space is about really having, training your own models. Okay, very often, really, what people would say, look, if someone gives you a name entity recognition model, say, oh, you can just reuse it for your project. Oh, it's basically saying, well, you need a binary classifier? No, I already trained another binary classifier. It doesn't matter on what data for what problem, but it's binary. It returns zeros as one, you can use it. So this is obviously ridiculous. If you look at any classification problems, people often make that mistake with NLP. Come and say, oh, no, this comes with pre-trained models for English. Okay, English has, or every language, really breaks into many, many different contexts we should be aware of. So, one example we're going to talk about is healthcare, partly because we do a lot of work in the healthcare space, but also really as an example of one specific domain that is very unique. Most people, myself included until like a couple of years ago, cannot read medical records that doctors write, because it uses clinical language, it also uses clinical vocabulary, and it has its own peculiarities. So what you need to do based on the core library is build extensions. Okay, so the core library is an open source library. On top of it, really, there are 2 things that you need in order to extend the library into a domain. You need data sets. And specifically, if you're in life science, if you're in medicine, there actually are a lot of pre-built terminologies and ontologies. Okay? If you think about it, the first ontologies that humanity built right, or of nature, right, can build ontology of all living things of the planet, ontologies of plants, ontologies of body parts, ontology of diseases, right? So specifically, healthcare and life science are pretty much the only domains in which you have this really rich pre-built ontology, which you should use if you have it. If you're dealing with politics or news or music, you'll have much weaker ontologies, right? Now you can have some people, but you'll never have a complete list, right? And then you need to augment it with word embeddings or other techniques. So one thing is the data side. The other thing that you need are the models themselves. Okay, and right, so you want to have algorithms, neural networks, and specific trained models for specific specialty or subspecialty or domain. Okay, and the company who does this as a commercial thing, but they're also very open about how they do it. So we're going to talk about some of the algorithms and how you can do it on your own. So what we're going to do is walk through really 3 or 4 sort of classic NLP tasks, look at the algorithms that are there, talk through how they are implemented in the library, and show you an example of how you can train your own domain-specific model for this case. So the first really NLP task that we want to talk through is what's called named entity recognition, which means that given a piece of text, in this case a medical paragraph, we want to be able to recognize entities. Okay, so when you say entities, the question is, okay, what kind of entities are you interested in? In this case, we're interested in problems, in tests, and in treatments. Okay, so around the left eye, test CT of the brain showed no acute changes. CT of the brain is a test. Okay, so what we need is we need to understand, first of all, we need to have some vocabulary or some external understanding that tells me that, okay, CT is a kind of test. We need some ability to understand, and in this case, CT of the brain is actually, is a noun, or noun phrase. It's within a sentence. It should come as one thing. We need what's called a chunker. A chunker will tell us that CT of the brain is not 4 tokens, it's actually one chunk, and we want it as one entity, right? And then we can mark it correctly. Acute changes is a kind of a problem. Left periorbital soft tissue swelling is one thing, right? Should be a problem, and so on. When we have a named entity recognition algorithm, so we want to identify the kind of entity, we want to identify the correct beginning and ends of chunks. Another thing that we'd want is we'd want the algorithm to be based on grammar, so that to the extent possible, it should also recognize terms it has not seen before. Okay, so the goal here is not only to do text matching to a dictionary. Okay, the goal is to come and say, look, if we talk about, for example, a fracture, okay, it could be a noun, it could be a verb, right? It could be, definitely it could be the name of a drug is also similar to the name of a place or person. Okay, we want the algorithm not to make that mistake. Okay, so if you tell me that this is a problem, or you tell me this is a person, or you tell me this is a location, okay, this needs to be a location. Okay, so if I'm meeting someone in Venice, I need to know so Venice could be a location. But if say I'm meeting Venice, in San Francisco, then Venice is probably the name of a person. And we want any algorithm to take it correctly in both of those cases, meaning it needs to understand the grammar and the concept of meeting someone somewhere in the English language. Okay, the other thing, the algorithm, if I'm saying I'm meeting Venice in San Francisco and Venice is the name of a person, the algorithm should know that even though it was never trained that Venice is the name of a person, never had a dictionary. Okay, so with NER, the goal is to train the algorithm really to understand some of the grammar, so it works well with unrecognized entities. Okay, that works really well if you're looking for people name, place name, organization names, nicknames, those kinds of things. For the healthcare space, basically there are separate academic workshops and separate research tracks for how you do NER for healthcare. One of the well-known academic competitions is the I2B2 competitions. They've had, basically, they were able to pay people to label data sets in 2010, 2012, 2014, and all of them had different types of NER tasks for different healthcare use cases. Basically, what we've done here in the library, we've taken a paper that was published in July 2017, which basically is the best of class result to date in this space, and productized it. The network that we have here is a neural network architecture that basically uses a bidirectional LSTM for the tokens, okay, I mean the words within the text that we are processing, and uses a CNN for characters, for character level recognition. Okay, So where the embeddings are fed into the bidirectional STM, then into there's the character layer for the CNN, and then we predict basically what are the actual entities that we recognize. Okay, and so the goal was to come say, okay, this is the state-of-the-art algorithm that we have. This is what we want the library to be able to implement. Okay, now the question is, how do we actually go do that? The way we've implemented it was actually using TensorFlow to build the network itself. Okay, but if you remember, the library itself, it runs on top of Spark. Okay, meaning it runs within the JVM directly. Okay, we wanted to get to a point where if you want to reuse the exact same graph, okay, but you want to train on your own data set because you have oncology data, you have pathology data, it's not exactly the specialty this was trained on. You wouldn't need to separately go and install TensorFlow and build a graph and do all of that. Also, if you want to reuse some of the existing pre-trained models and really you just want to do inference also, you do not need to install TensorFlow or anything else. And for that, there are a couple of interesting data engineering tricks that had to be done. Basically using the TensorFlow GNI engine and bundling some of that sort of within the library itself. So when you run the library, basically, you do not need to install anything else. You can build a Spark NLP pipeline, tell it, okay, train a deep learning NER model, and it would do the training, and you'll see an example. The other thing, obviously, you can tell it to do inference, and it does it well. So other than this kind of basically very specific type of TensorFlow integration, the other thing that we had to take care of was actually distributing the models itself. Okay, and the other unique thing that this gives you is that inference here would actually scale. Okay, so now if you want to apply NER, either in a server setting, you can use light pipeline and do things sort of on a one-off basis at with very low latency, or do this at scale on a cluster. You have those things basically out of the box as well, right? Because all of that, really how we load the model, how we cache it, how we distribute it, is taken care of for you in the backend. Okay, so now I'll hand off to Alex to just go through the notebook of how training NER works. Sorry, apologies. Go for it.
Okay. So let's see. This notebook, though, wasn't checked in after being run, so we're just going to be going through the code. We don't have the example of the output, but again, you can just check out this notebook along with the Spark NLP project, and you can run through it and check it out for yourself. Okay. So here we are doing our imports again. In this case, this notebook is assuming Spark NLP is already available. Here we're pulling out this data set, and then we're pulling some word embeddings to use, as David was describing in the architecture earlier. So let's see. So now we build our Spark session. So if you remember before, we have the document assembler, so that's the thing that's going to take the text of our documents, the things that contain the named entities that we're looking for. It's going to build a document out of them, do the sentence splitting, we're going to do the tokenization, and then we want to have the tagger go through. So this is where all the cool stuff is happening. Now, the way this sort of works is maybe a little bit different than how some other algorithms done on Spark ML work. Rather than us, feed in the data set directly and have it fit, here you see that we have it being fit on the side here. So what's happening with this annotator is that we have that TensorFlow graph defined and serialized. It's then loaded. This data is then taken and it's trained. And then we have a tagger built. And then we have the tagger we have something here that will take the output of that tagger and make it more useful to us, make it to this NER span. And then we have the finisher. So what will come out of this pipeline is just I believe, an array of the NER strings. So that afterwards, if let's say you want to do classification, so let's say we have, what was it? It was problems and what was the other class? Problems, tests, and treatments. And you have the different things in there, different problems, tests, and treatments. So if, let's say, we had some sort of classification, we wanted to maybe identify whether someone was going to be admitted, right? So we have the problem, what they came in and complained about. We have whatever home remedies they tried, and then whatever initial tests the doctor did. And then we want to figure, okay, is this person going to be admitted for an overnight stay? So now we have a classifier. Well, we run it through. We get just those named entities out, because we don't care about necessarily all the other words. Maybe we're just limiting it to this vocabulary. And then we could take the output of this pipeline and give it to a classifier. In this case, though, we're just going to be building a sentiment classifier. Let's see. So here we're loading this data and then processing it through the pipeline. That gives us a model here. So now we have the output for our data, and we can save that. And if we wanted to, we could use it for training other things. So any questions on this?
Okay. So really the important thing to know is really what you need. Provide your training data, provide your test data, provide your word embeddings. That's it. Right, and you have really this, things that really came out of academic research last summer, and you have the ability to go and build a deep learning network, and then use it pretty much immediately within a bigger pipeline that you are building. So the next task we want to talk about is entity resolution. So entity resolution is a different type of NLP task. Although it's somewhat similar for NER, so you don't know really which one you need to pick for each specific use case you have. With entity resolution, we want to look at the text. So for example, we look at renal failure and we say, okay, this is, it's a problem. It's similar in the sense that, yes, we want to find it within the text, only in the right context. We want to make sure we chunk it correctly, so we take the maximum set of words that's actually relevant. But now we want to actually give it an identifier. Okay, meaning I don't just want to know that this string is this thing, I want to know exactly what this is. In the healthcare case, it means that I want to map it to a SNOMED or RxNOR or UML-SID. So I want to map it to existing taxonomies. Okay, if you think about the more general case, for example, I want to know that Alex and David are speaking today at Spark Summit. So Alex and David are people, and Spark Summit is an event. Okay, but I don't just want to know that Alex is a person. For example, I want a link to the Wikipedia page, or I want a link to the LinkedIn page, right, of that person. So I want some identifier, okay, because I want to know specifically which Alex this is, okay, and I want to have really an ID that goes with it, okay, because really this works when what you're trying to do is really build a knowledge graph. Okay, and knowledge graph means that you're trying to look, for example, at meetings between people who worked on what projects. You look at financial statements and look, oh, this company bought a stake in this company, or they appointed this executive to this position. And you need to build this graph of really well-defined structural entities and the relationships between them. Okay? So for that, you need entity resolution. Because basically, on top of NER, you also need to really be able to resolve which Alex we are talking about, because there's quite a few of you. So we need to know which one. The downside of entity resolution compared to NER is, of course, here we cannot expect to map to things we have not seen before. Okay, so if NER, we can come and say, look, if this looks like a person, because grammatically you use it only at a place where a person would be, okay, then NER should get it here, unless I know what the ID is, because unless I can map it to some dictionary for this, you would not get it. Okay, so entity resolution works well when you're building a knowledge graph and the entities are there, right? And basically you're just trying to actually now begin to build the edges of the graph, right? And see how those, learn things about how those entities interacted from free text. So entity resolution is a separate problem algorithmically, which means that there's a separate line of research work that was done to really trying to see, okay, what is the state of the art for entity resolution in general? What is the state of the art for entity resolution in the healthcare space? Like many other things in the in the NLP, ML, and vision space, the state of the art has moved into the deep learning space, and this is in October 2017, so really less than a year-old paper that really gives the state-of-the-art results in this space. And like many papers that have come out in the past 2-3 years, a lot of it is, we pretty much know that deep learning can do more because, it can just basically pick up more signals and have enough data. So the question is really, what's the correct network architecture? What are the hyperparameters that are optimized for a specific domain or specific problem? And really, what's the best way to put it together? And you have the paper here, and we'll make the slides public, or if you want, just email us. We'll send them to you. And you can look at the numbers. Basically, what we've done with the library, we don't show the code, but it's very similar. Also, there's an entity resolution annotator, and you have the ability to either use what's there for healthcare, or you can definitely go and train your own. Similarly, it's basically, you have from your side, it's several lines of Scala, Java, or Python code that you need to put together, and then you can either call the training and train on TensorFlow in the backend, or apply either training or inference at scale as you see fit. Okay, so that's another just task that is there and has been implemented. The next task that is in the library, and there are actually 2 separate implementations of this, is assertion status detection. And assertion status detection is grammatical task of understanding basically, when I'm making an assertion, what kind of assertion is it? Okay, so in the healthcare space, it's really important to tell between Jane has the flu, Jane does not have the flu, Jane complains about having the flu, which means maybe she has it, maybe she doesn't. Jane shows flu-like symptoms, okay, or Jane test came back negative for flu. Okay, so I really need to know whether something is positive. Look, here's a positive diagnosis, right? Or I'm giving you this medication, versus there's a negative diagnosis, okay, versus the more common case, which is a maybe. It's like, well, it looks like you have the flu, but I'm not going to run the test, just, go home, drink tea, right? Or all the cases are conditional. Conditional means something will happen if you don't do something, or something only happens, only feels pain in the morning, right? So things that happen only under certain conditions, okay? Other than the 2 other things that are usually wrapped under this problem are being able to differentiate between statements about the patient versus statements about other people. Okay, so if Jane's older brother had the flu, last week, but the 4-year-olds and 3-year-olds and they share the same room, then okay, it's actually relevant because maybe that's why Jane has got the flu this week, right? But we need to know that this is a statement about another person. Okay, and of course, in general, family history is relevant, but you need to know that it's family history and not the patient's history. The other thing, the last thing that's very important is to understand time. Okay, and obviously, this is also something that's very domain-specific. If you're looking at meetings between people, right, because you're in cyber terrorism, that you need to know if something happened 60 minutes ago, 30 minutes ago, or such. If you're dealing with companies and acquisitions, you're looking at a quarterly basis. In healthcare, usually what you care about is really only 2 things: whether this is why you came to see me today, or whether this is ancient history. Right, so like, are you having knee pain now, or do you have a chronic history of knee pain, but you came today for something else? Okay, so obviously, if we have a statement but it relates to history, it's very important to know it is history. Okay, if you don't have this algorithm, come say, oh, no, patient has a severe case of blah, okay, of flu, right? If you don't know it, it says last year, you're going to extract a feature here that's very wrong, because that's not what's actually happening. And you make decisions based on that. So the goal is to build an annotator that looks at the text and basically assigns a scope. Okay, so I want to say, okay, Jane complains about flu-like symptoms. You want to come say, okay, this entire scope, this entire part of a sentence, in this case a full sentence, it could also be a part of a sentence, it's under a speculative assertion status. Okay, so that later on when we have, so we may have some entity resolution here, we have some part of speech, we have the now we're going to have the scope of the assertion status. From that, we can start extracting features, okay, or running queries. Okay, show me all the people, or okay, it's a really important feature. If he actually has the flu, right? If she complains about throat pain or fever, okay. But I need to know that those are actually present for the patient at the present time. So the library is actually quite unique in the sense that it does implement a deep learning algorithm for assertion status detection. The paper that we have is a 2011 paper. That has really some of the best results in the field. We haven't actually found deep learning papers that are specifically cover all the aspects of this problem. So we actually implemented a deep learning variant of this algorithm. It actually performs slightly better in more context. And that's really what, that's the graph that comes with the library. Okay, so obviously the models are licensed, but you're free to train your own, and that's all free. So and the code and the graph itself comes with the library itself, with the open source library. So you're welcome to do that. And definitely gives you state-of-the-art results in terms of how accurate this gets, and how accurately we can really understand those contexts correctly. So now Alex will walk through that code piece that shows you how you use the deep learning-based assertion status detection, which is here. So go ahead.
Okay. Okay, so we do some of the stuff before. We're doing our importing. Again, this is available in the GitHub repo for Spark NLP. So here we're creating our Spark session. We're running it locally. So we pull our data set. Now, if you notice this one, there's no mention here of loading external data set. That's because this one is trained directly on the data set we're going to give the pipeline. So the data set we have comes with the labels, and we're just going to be reading in the sentences as documents. So if you notice here, we're not doing any like the sentence segmentation or tokenization because in this case, it comes in with sentences. So we're just going to run directly the assertion identifier. So here we just have the document assembler, assertion, finisher, pipeline, done. And that's it. So then we have our data set here. You would run fit on it. And then after that, if you notice the finisher, let's see. So it doesn't have like specific, it's just taking the assertion column so that afterwards you will know what the assertions are that it's found. So the way it works is that the labels can be anything. So in this case, maybe it's a positive, negative, speculative, conditional, but you could have other classifications in there as well. And what it will have when it has the set include keys here, that will inform you as to what that annotation is identifying. So yeah, we run our model, then we get our assertions out. And probably if you're getting assertions out like this, you're probably going to actually use that to augment something like what we did previously. Like maybe you get out pieces of vocabulary and then you figure out what assertions apply to them, because you don't want to treat the finding of has cancer and does not have cancer as the same feature. So this would probably be combined with like some entity recognition. Yeah, and again, this one, just to reference, this one also is loading its graph from a serialized TensorFlow graph and then running it in a distributed fashion. Any questions? Oh, how would we combine it with the entity recognition and the entity resolution we talked about earlier? So the idea is that, let's say we have our documents that we're pulling through problems, tests, and treatments. If, let's say, we're trying to find people, let's say we're trying to find examples of side effects with a particular drug. If the patient comes in and complains about let's say the patient has taken this drug for a period of time, and the doctor asked whether they're experiencing any of the side effects, and then the doctor writes down, let's say the side effect is nausea, and then the doctor writes down the patient is not suffering from nausea. Well, we wouldn't want our model to just see, oh, nausea appeared in this document. So we would want to take the assertion, mark that named entity we resolved as negative. So rather than just having our feature be nausea in whatever we're putting into our model, it would actually be negative nausea. And then there'd also be maybe a feature for positive nausea. So that's how you combine it.
the second question, please?
Sure. So you're using TensorFlow as a micro library. So how can you use TensorFlow without using it as a dependency?
Without using?
As a dependency.
As a dependency, sure.
The graph is saved in a serialized format, and we have something that will just load a TensorFlow graph, and it's not trained with TensorFlow. It's trained with deep learning 4J?
Oh, with TensorFlow.
Yes, with TensorFlow.
It's in the jar.
Oh, so yeah, so it's trained with TensorFlow in a separate place, and then you just save that graph and load it.
Yes, and to your earlier question, yes. So if you're looking to change the graph, yes, you can definitely do that. But then to edit the graph, you cannot do it from the TensorFlow or Java API. You do need a Python version to do that. So if you want to play with the graph, you need to do that. Okay, but here, yeah, basically the jar here includes the correct version of whatever we need out of TensorFlow to do training and inference. Okay, so we are at time. So one last point is, all of this is online. So if you Google Spark NLP, you get to this web page. You have the getting started. You have full documentation. The notebooks we went through are in the example section. Other than that, there's an active team and community working on this. So you're welcome to just join the Spark, the Slack community. People answer questions daily. If you find bugs, open GitHub issues. We fix them. There are releases on average every 2 to 3 weeks. So please give it a shot and let us know how it goes. Thank you very much.